Hello again. Welcome. Today we will talk about the tabular simplex method. In reality, if you have understood the mechanics of the algebraic simplex method, then you have understood the simplex method. It doesn't matter if the simplex method is algebraic, tabular or in matrix, the mechanics is always the same. The only difference is the presentation form. Let us start by overviewing some concepts and by recalling the steps of the algebraic method. The problem we saw the previous session is the following. And the first step is to transform each inequality into an equality. When the constraint is less than or equal to, we add a slack variable. And when it is a greater than or equal to, we must subtract a surplus variable. Usually, we denote these variables with the letter S. I will erase the original problem, to show you how to represent these equations in the tabular form. In the tabular method we create a table that contains a column for each of the variables. In the gray row we will place the objective function, and in the other rows we will place the constraints. Let me start by placing the first constraint in the table. The first constraint is 2x1 plus x2 plus s1 equal to 20. In the row corresponding to the first constraint we will place the coefficients of the variables. If a variable does not appear in that equation, its coefficient is 0. In this way, the row that corresponds to the first constraint will have the following values. Now we will place the values of the variables in the rows that correspond to the second and third constraints. Observe that the values found on the right-hand side of the equalities appear in the last column of the table. To write the objective function following the same pattern, we must rewrite it in the following form. Now we are ready to place the equation in the table. Recall that in the algebraic method, we tried to find a solution to the system of equations. To recognize the variables that have a value different from 0, versus those which are 0 valued, we looked for the variables that appeared in only one equation with coefficient 1. In the simplex table it is even easier to find them, since these variables will have the coefficient 1 in one row, and zeros in the other rows. These variables are called basic variables. And in this case, S1 will be basic in the first row. S2 will be basic in the second row. And S3 will be basic in the third row. If S1 is 20, S2 is 18, and S3 is 8, then the value of the variables x1 and x2 is 0, and therefore the value of z is also 0. We will try to increase the value of z, by making x1 or x2 greater than 0. To know which of these two variables should increase, we observe the objective function row, and search for negative numbers. If this is the case, we select the smallest of them. This means that x1 will be transformed into a basic variable and its value will be greater than 0. Now we must look for which basic variable x1 will substitute. To find out, we must know which constraint limits the most the increase of x1. Recall that in the last video we said that if the coefficient of a variable in a constraint is 0, or negative, the value of that variable could increase with no limits in that constraint. But if the coefficient of that variable is positive, then a simple way to identify up to what value that variable can increase in that constraint is to divide the value of the constant by the coefficient. Now we select the row with the smallest value. This means that the variable x1 will be basic, and s3 will no longer be basic. The construction of the second table, starts considering the number found in the intersection of the variable that enters the basis, and the variable that leaves the basis. Now we will start the construction of the second table. Our basic variables will be s1, s2 and x1. We start by placing the row of the entering variable in the second table. This row will be the same as the one in the previous table, divided by the number indicated with the red circle. Since in this case that number is 1, then the row in the second table will be exactly the same as the row in the first table. This row is known as the pivot row, and I will mark it with the red color. Recall that for the variable x1 to be basic in the third row, its coefficient in that row must be 1, and must have 0 coefficients in all the other rows. This means that the values of -7, 2, and 1, that appear in this column, must be transformed to zeros. Let us start converting -7 to 0. To convert it to 0, we multiply the pivot row by the negative of the number, and then add it to the original row. That is, we multiply the pivot row by 7. And now, we add it to the row where the -7 appears. And place the answer in the objective function row of the second table. 0, plus 1. 7, minus 7. 0, minus 4. 0, plus 0. 0, plus 0. 7, plus 0. And 56, plus 0. In the same way we converted the -7 into 0. Now, we will convert the 2 into 0. We start by multiplying the pivot row by -2. And now, we add it to the row where the 2 appears. The result of the sum will be placed in the S1 row. We are almost done filling the second table. All that remains to be done is to transform into 0 the one that appears in the S2 row. We multiply by -1 the pivot row. Now we add it to the S2 row. And the result is placed in the new S2 row. Now the second table is complete. Again, we must observe the objective function row. We must find out if negative numbers still exist. If so, we select the smallest of them. This means that the variable x2 will enter the basis, and now we must determine which of the variable will leave the basis. Recall that the new entering basic variable will enter in the row corresponding to the constraint. Welcome again. Today we will talk about some other characteristics of the simplex method. In particular about the use of artificial variables. These type of variables are regularly used when the model includes constraints of the type, greater than or equal to, or when equality constraints are included. Allow me to explain why the artificial variables are needed. Suppose we have the following problem. As I had commented, when we have a constraint greater than or equal to, instead of adding a slack variable, we must subtract a surplus variable. In this way, we will arrive to the following system of equations. If we create the simplex table for this system of equations, we will obtain the following. If you observe the table, you will realize that the variable s1 is basic in the first row. The reason why this variable is basic in that row, is because its coefficient in that row is 1, and in all the other rows its coefficient is 0. For the same reasons, s2 is basic in the second row. But if you observe carefully, you will find that there exists no basic variable for the third row. S3 cannot be basic for this row, since its coefficient in this row is -1. This problem cannot be ignored since the simplex method cannot be executed until we have a basic variable in each row. This is the reason why we need artificial variables. To have a basic variable in that row, we add an artificial variable to the third constraint. By doing this, we will have a variable with coefficient 1 in the third row, and its coefficients in the other rows will be 0. But if we only add the variable, it is possible that when we get the final solution of the problem, the variable A3 has a positive value. And if this happens, it is possible that the third constraint won't be satisfied. Therefore, the problem now consists on doing everything possible to make this variable equal to 0 in the final solution. One way to force this variable to have a value of 0 in the solution, is to assume that this variable causes a very big loss of profit. And then the method will force the variable A3 to have a 0 value when the problem is finished. To achieve this, we will say that the coefficient of A3 in the objective function is -m, where m represents a very big value. This is the reason why this method is known as the Big M method. I will erase the table and the original problem, and I will keep the modified system of equations. Now, we will construct a new table for this problem. Observe how the variable A3 is almost a basic variable in row 3, since we only need to transform its objective function coefficient to 0. To make the coefficient 0, we follow the usual steps of the simplex method. We will multiply by -m the A3 row, and we will add it to the objective function row. When the A3 row is multiplied by -m, we obtain the following. Now we add the objective function row. And we obtain these expressions. This row represents the new objective function row. Our new table looks like this. Recall that m represents a very big value, for instance 1 million. Therefore, when we scan the objective function row to look for negative values, we find 2 values. And the smallest of them is -2m-4. Now, we know that the variable x2 must enter the basis, and we must find the leaving basic variable. Recall that to do this, we must divide the values of the right-hand side column by the values of the coefficients of the entering variable. And we select the smallest of them. The variable that enters the basis is x2, and the leaving variable is a3. Allow me to rearrange the tables. As I was saying, the entering variable is x2. And the leaving variable is a3. The number in the intersection of both arrows is fundamental, since the construction of the new table will start considering this value. In the next table, the basic variables will be s1, s2, and x2. We begin by transferring the row of the entering variable to the new table. This row will be the same as in the previous table divided by the number indicated in the blue circle. By dividing the row by 2 we obtain the following numbers: 0, 1/2, 1, 0, 0, -1/2, 1/2, and 6. We will transfer this row to the new table, and I will highlight it in red, to indicate that it is the pivot row. Now, we will use this row to convert to 0 the other numbers in the x2 column. To convert the -2m-4 to 0, we must multiply the pivot row by 2m plus 4. This multiplication will give us the following results: 0, m plus 2, 2m plus 4, 0, 0, minus m minus 2, m plus 2, and 12m plus 24. Now we add this to the objective function row and transfer the result to the objective function row of the new table. Next we will convert to 0 the next number in this column. To convert that number to 0 we need to multiply the pivot row by -1. When we do this, we obtain the following. And we add the S1 row. The result of the sum will be the new S1 row. To finish this table, we only need to convert to 0 the next number. Again, we must multiply the pivot row by -1. And add the S2 row. And the result will be placed in the S2 row of the new table. Now that we are finished with the second table, we must look for negative numbers in the objective function row, and select the smallest of them. Now, we will divide the numbers that appear on the right-hand side of the table, by the numbers that appear in the x1 column. Recall that dividing 14 by 3/2 is equivalent to multiply 14 by 2/3. In the same way, to divide 12 by 1/2, is equivalent to multiply 12 by 2. And to divide 6 by 1/2, is equivalent to multiply 6 by 2. I will place these numbers at the end of the table. The smallest of these numbers corresponds to the S1 row. And we conclude that in the next iteration, x1 will enter the basis and S1 will leave the basis. Now, we must convert this number to 1. Allow me to arrange these tables again. Our new basic variable